As we focus on quadratic functions and their inverses, we first just want to look at this graphically. So I have a quadratic function, x plus 4 squared plus 1, and we could graph that using transformations. It moved left 4 up 1 and has that regular quadratic shape. It was not vertically stretched or reflected or anything. So we can find points on this graph and plot the inverse to get the inverse graphically. There's the vertex here at -4, 1, so its inverse would be 1, -4. There's another point over here at -5, 2, so we would have a point at 2, -5. You'll notice there's another point at -3, positive 2. So the inverse there would be 2, -3. And we keep graphing each of these inverse points. So you would have one at 5, -2, and at 5, -6. There was a point up here at -1, 10, so we have a point at 10, -1, and another one at 10, -7. This inverse graph looks like a parabola, but it is a sideways parabola, and that's not the perfect line. So when we think about that inverse graph, it is a sideways parabola, but would that represent a function? And no, it does not represent a function because it fails the horizontal line, it fails the vertical line test. So if it's not a function, then it can't be written as an inverse function. The inverse graph is not a function. But if we restricted the domain of that original function, then it could have an inverse. So in this second question, we have create a domain restriction for the function f of x so that it's 1-to-1 and non-decreasing. Now, non-decreasing is a weird way to say that we're increasing, but technically it's not increasing right at that vertex, so we're saying the words non-decreasing. If we focus only on the right side of that parabola, then it would be a 1-to-1 function. So I could even cover up that left half and see now we do have a 1-to-1 function. It is 1-to-1 and non-decreasing on the domain of -4 to infinity. So whichever way we need to write it, -4 to infinity or x is greater than or equal to -4, that has a inverse. And if we were looking at the inverse, it would be the top part of this parabola. Top part of the sideways parabola. So let me cover up the bottom half. These two sections are inverses of each other. So a quadratic function can have an inverse. We just have to create a domain restriction first, and then we can find its inverse. That's what's going on in this next part. It says sometimes a function will need a domain restriction so that it can be 1-to-1, and then we can find its inverse. In the graph we have below, we want to use that function to look for a domain restriction if needed and graph the inverse. So I have a radical function actually, and if I needed to graph that one, I would just use my transformations. It moved left 3, it was vertically stretched by a factor of 2, and it went down 5. We find points on that radical square root graph and graph the inverse. So there's a point at -3, -5, which means I have a point at -5, -3. And we keep finding more points. So -2 is at -3, which means -3, -2 is a point on the inverse. it looks like the y-intercept is roughly 0, negative 1.5. So the inverse would be negative 1.50. The x-intercept is a little bit after 3, so it might be 0, 3.1 for its inverse point. There is a point at 6, 1, so I can put a point here at 1, 6. And we just continue finding more and more points. But the inverse looks something like this, and it is still that reflection over the line y equals x, so you could draw in your reflection line. If we were discussing the domain and range of the inverse, this was our inverse function. So the domain of the inverse started at negative 5 to positive infinity. The range of the inverse would go from negative 3 to infinity. So we can graph that function and describe its inverse domain and range. As we're looking at that graph is half of a parabola. So it is a quadratic function, just limited to one side. We're going to look at a few of these without a graph. So we're going to find the inverse algebraically and restrict the domain if needed. But it is always helpful to kind of think about what this would look like graphically. So if I did f of x equals the square root of x minus 2 plus 1, that function shifted right to up 1 and would look something like this. So the domain of f would be 2 to infinity. The range of f would be 1 to infinity. We want to find the inverse algebraically this time. And when we were doing that earlier, we would swap our inputs and outputs. So we're going to swap our x and y. This becomes x equals the square root of y minus 2 plus 1. To get y by itself, we need to get rid of the 1 before we can square both sides, because we need to isolate the radical. So I would subtract 1 and get x minus 1 equals the square root of y minus 2. We can square both sides now. When I square both sides, we end up with x minus 1 squared equals y minus 2. So y is almost isolated. We just have to add 2 to both sides. X minus 1 squared plus 2. And there's our inverse function. It's probably easier to leave this in vertex form because I can see the transformations. The inverse would be a quadratic function shifted right 1, up 2. But if we think about that graphically, we hopefully realize that they don't look exactly the same. And that's because this quadratic function is not truly the inverse. I would need to specify its domain. And that means for this one, the inverse of this square root graph would be the right half of that parabola. So that would be all of the parabola as long as x is greater than or equal to positive 1. Another way that you could write this function would be in standard form. So if you had written it in standard form, though not required, you would have x squared minus 2x plus 3, but you would still need x is greater than or equal to 1 with it. I prefer the transformation form, but you can do the standard form. It doesn't really matter. All right, and for number 2, we have a quadratic function. F of x is negative x minus 1 squared plus 2. And I've given you a blank here because I want you to think about what that domain restriction should be. I know that this is a quadratic function, so it's not one-to-one, and it would have to have a domain restriction. But if we were to graph this, this went right 1 up 2 and was reflected down. So this parabola is not one-to-one, but if I limited its domain, then it could be one-to-one. So we have x is greater than or equal to some number. This would be one-to-one if we were looking at greater than or equal to +1. So we're going to focus on that. Now it could have said less than or equal to +1 as well, and that would just give us a different domain, which would in turn give me a different inverse function. So for this one, we're going to solve for the inverse by swapping our x and y's. This becomes x equals negative parentheses y minus 1 squared plus 2. To get the y by itself, we're trying to isolate the squared parentheses. That would mean I need to first subtract 2. That becomes x minus 2 equals negative y minus 1 squared. That negative is a -1, so I can divide everything by -1 to make that negative x plus 2 equals y minus 1 squared. Then we would square root both sides. When we square root both sides, we have a positive or negative square root of negative x plus 2 is equal to y minus 1. I can add 1 to both sides. And so we actually end up with two different functions. One has y equals the positive square root, and the other one has the negative square root. And this is where we're talking about this domain restriction. Earlier, we had to graph those inverse functions. Let's see if I can find that graph. Oh. All right, I already lost it. Here we go. We have an inverse graph of a quadratic function, and it became the inverse was a sideways parabola. And that's two different square roots. This is a positive square root of x, and this is a negative square root of x. So the top half represents a positive square root. The bottom half represents a negative square root. The top half was the inverse of the right side of a parabola, and the bottom half was the inverse of a left side of a parabola. So when we were working with the right side of the parabola here, we need to decide if we need the positive or negative square root. Okay, so it's based off that quadratic's domain restriction. We restricted it to the right side of the parabola, which means that f inverse of x would be the positive square root of negative x plus 2 plus 1. And we can put in that domain and say, well, this would happen as long as x is less than or equal to positive 2. That's a little bit implied because of that square root, but when we think about the domain and range of f, the original domain of f was 1 to infinity when we restricted it, and the range of f was positive 2 down, so negative infinity to positive 2, which is all the values that are less than or equal to 2. So that range of f is the same domain of the inverse. Those are a little bit more complicated and they take some more practice, so there are some more examples in this Check Your Understanding.